rotational axes and joint velocities, we need to talk about velocity propagation. What does it mean? So if you assume a robot, I'm going to use my arm because it's something you can also check on your body, and then it resembles articulated robots, right? So if these are my joints, if you want to know what's the velocity at the end effector, if you propagate, if you know the velocity here, then you know velocity here, you can say that they're relative, right? So this would go fast, like 2 meters per second or whatever, but depends on what the velocity of this one is, it would impact, right? So the velocity propagates through the joint. We're going to find each velocities and we're going to consider them all together. So we're going to simplify a problem that let's walk the joint by joint and then put this together to create that mapping, because the mapping is the same thing, right? How each of those impact the velocity of the end effector. So we're going to use the same idea. So if you wanted to find the velocity here, you're going to start walking from 0, 1, 2, and n. Now, the main difference before kinematic is before kinematic, we calculated everything with displacement, right? For velocity kinematic, it's the relative velocity. So we're going to calculate joint by joint. So the current joint, you're switching to previous joint. Then when you walk, you have a new previous joint. Does that make sense? So if you're in joint 1, your previous joint is 0. Then you go to 2, your previous joint is 1. Until we get to the answer. Then we put them together and it becomes our final velocity. We will have 2 kind of velocities. Again, linear velocity, angular velocity. I feel like you already know, okay, I have to consider all the joints. Are they creating any linear velocity or are they creating any angular velocity? Same thing that we talked before. We're just building on top of our previous knowledge. These are, none of them are new. It's just how we use them in our advantage. So this is a general case between 2 joints, joint I and joint I plus 1. We are going to call our angular velocity omega I and the linear velocity vi. So this is a general case. We are assuming there are 2 velocities. It might not be. One of them might be 0, right? You're generalizing it. You're going to say also that the coordinate of these 2 joints, they have an opposite, pi plus 1. If they were on top of each other, pi plus 1 is 0, right? So we're going to assume that it's not 0. Then the other joint will be joint I plus 1. We have omega I plus 1 for the rotational velocity of that joint, and vi plus 1, the linear velocity of that joint. Now, omega I plus 1 and vi plus 1 are impacted by this. So there will be a trace of vi and omega I in that. But then what if this was a rotation? It was a like our joint rotated joint. We introduce omega capital I plus 1 to be the velocity of that joint itself. And the lowercase omega I plus 1 is the velocity that could be impacted by this. So few things here that you need to pay attention. So these are basically, we are introducing our variables. So every time you're talking, because I'm going to say omega I and omega I, one is in uppercase, one is lowercase, right? It's up to you to figure out which one I'm talking. I will write them lower and uppercase, but when I read them, they're the same. So it's hard to distinguish. But if you're following me, you'll be able to recognize. So for this one, let's say this is my first joint. Theta dot is the angular velocity, correct? If this was a R joint, theta would be the position, the angular position, and then theta dot is angular velocity. This joint could also be a prismatic joint, right? Because we don't know what the joint is. So this method, we will establish the equation for a general case, and then we're going to say, okay, now this is a rotary joint, it will look like this. It's a prismatic joint, it will look like this. So you need to remember the equation one time. All right. So for the linear velocity for joint VI plus 1 for the next joint, for this joint. What component can there be for the linear velocity for this setup? Knowing that we don't know what this previous joint is. Could be a prismatic, could be an angular. So what component would you expect to see in the linear velocity of that joint I plus 1? I heard something. We are gonna write, there are gonna be few things, this plus this plus this plus this. I'm gonna write what they are. What's the first thing you know? So what does it mean? It means that I'm not gonna borrow that. I'm gonna use this. So let's say my bag is swinging, right? And I'm going forward. So if increase time and this and look at the corner of this. So I'm moving forward and this is swinging. What would be the linear velocity of this? What impacts the linear velocity of this point? This joint, right? And I'm this prismatic. What would impact the linear velocity here? So I'm going to want to change it. Well, my linear velocity, right? Thank you. So what is the linear velocity of joint I? VI. So we know that if there was a VI, it will show up in VI plus 1. It will impact that. Because this is relative velocity, right? So one item would be VI. Then you remember if this was not a prismatic joint, let's say, use the bag again. Let's say this was a rotation. What velocity you will see here? This was rotating, right? Rotation. Omega cross product of the distance, right? So there could be omega I cross product of pi plus 1. We call this distance pi plus 1. So what else? So now these two are because of the previous joint, right? At joint I plus 1 and its own frame, what linear velocity component could there be in case of prismatic, in case of a rotating joint? Looking at this will help you. The I plus 1, it could be a prismatic joint. It could have a linear velocity, right? Okay, what if it was a rotary joint or joint at its own here? This could be the I plus 1, could be a prismatic joint. We don't know what joints are. We're assuming for general case. If it was a rotary joint and you wanted to know if there was a linear velocity in that same frame from the angular velocity of itself, would there be one or not? No. Why? Because there is no distance, right? So at its own frame, there is no linear velocity because of its own angular velocity. So you're done. So now, doesn't matter what robot I did. So this is kind of like how you code it also. When you solve the robot, you say, how many joints do I have? User, 3. Okay, let's walk. I'm going to write a code that solves this for 2 joints, and I'm just going to have a for loop and go between the joints. 0 to 1, 1 to 2 to 3. So this is a good method, called explicit method, because you're basically writing your program, your code. You're using I plus 1, so it doesn't matter what joint it is. You just need to know, just need to get from the user what is the kind of joint you're using. Does that make sense?
We have to be on both sides though. How would we?
No, we are starting from one fixed frame and you walk by. And then at the end, the velocity is with respect to this fixed frame.
Okay.
Yeah. And if you said, no, I want the velocity respect to something else, you want from the other.
So probably have this policy for break.
Yes, so the velocity in its own frame is because of whatever happened before plus its own set, right? So because if you have angular velocity in your own frame, there's no distance, so basically the axis passes through the origin. There is no induced linear velocity, there is no centrifugal force, so you only have linear velocity because of a prismatic joint previous frame, a revolution previous frame, if there's an offset, or if this was a prismatic. That's all. So in this method, you're putting the work up front. You write this and then that's the you're done. Right? Now let's do this for our angular velocity. Omega I plus 1. 1 is omega I from the previous frame, right? Plus, let's say this was theta dot I plus 1. You have theta dot I plus 1. It's the angular velocity of that frame, right? Now, you remember every time we talk about angular velocity, we need to say which direction, because it could be in any. So we're gonna put which way is the z direction. And this doesn't change anything because it's a unit vector. It just tells us the direction. So when you put them together, one velocity in this direction, one is in this direction, one is the other. At the end, you know all the direction that you will have angular velocity. Right? Now, we will call this capital omega. So capital omega has the direction of the velocity in it. It has the axis in there. So for this would become omega I plus omega capital I plus 1. And then you might say, so how about that first one? Well, for the first thing, you have that. And then for the other ones, since omega I includes this omega I plus 1, you have the direction. Right? So the direction will carry as you go forward. So this is really, really useful, and you need to have it on whatever cheat sheet you're preparing for yourself for learning or working on the code for not this assignment, but for the next one. Now, you asked, I'm using it with respect to that frame. What if I want it somewhere else? So we can use rotation matrix. So you will find this velocity in with respect to, let's say, you start from fixed frame, you're walking that way. So it was a good question why we're walking that way. Because once we have it with respect to this and we walk that way, if we wanted to change, we just use rotation matrices and then it converts. So we don't need to do extra work. So we can write V in n frame, omega in n frame would be R 0 respect to n. Here is 0, 0 R respect to n. Okay. Equal, no, times, sorry, V n in its own frame. So I'm gonna put n here, so, and here's 0. So if you wanted to find that velocity in a different frame, all you have to do is find the rotation between those frames. Maybe you want to find the velocity of joint 3 in the position of joint 2. How does joint 2 sees the end effector velocity moving? Because why do we care about velocity at different places? When we have dynamic, when we talk about dynamic, what does velocity will give us? Momentum, force, right? Learn if you're braking our actuator, right? If there's too much torque on it, how do you calculate? Okay, I'm gonna see how many joints and length are after this actuator, and I want to see what's the torque. And I check the torque that this motor can sustain. If it was more, it's gonna break. So when you're designing your robot, you don't have to use all the same actuator. Your latest one probably can use a weaker actuator than your first one. The first one has to tolerate all the torques. Does that make sense? That's why we need to know this. But you don't need to have this relation for all of them. You just have a general torque. You find it with respect to baseline, and then you can walk and convert them. Right? So this actually happens if you are expecting the motor. Either you over design and say, okay, let's just pay $500 for every joint, you're gonna be safe. Or I'm really tight in money, I need to pick the right motor. Then you need to know the torque that each needs to sustain, plus some percentage of being safe there. Now, example. You literally can do this example because that was the only equation you needed. We did this last class using direct method, right? You had to find the equation and all that. Now imagine this has 3, 4, 6 joints in there and say how long that equation is going to be. You'll see that this is a lot easier. So we're going to work this together, but I want to show you your class participation. It's just one extra point, right? So if you don't understand this, what you're doing right now, you'll have problems doing your class participation. This is due Monday concept. You have weekend to go over and solve this, right? Now, a little bit of review on quick. So this was the velocity kinematic, right? J is your Jacobian. We want to find the velocity kinematic expression for this robot. In order to find it, I need to find what J is. What is theta dot? Do we know what theta dot is? Theta dot is theta dot 1, theta dot 2, right? Because I have only 2 joints, correct? And what is x dot? Is the velocity of your end effector, right? We see that in the 2D, we find in x direction and y direction, then we're good. So all we have to find is that J. What's J gonna be? Now, if I remember someone asked about this, what if I wanted to know what are the other velocities, like all 6 of them, right? So if we write this as x dot, let's say y dot, z dot, and then you have theta of end effector. Well, I'm going to say theta in x direction, y direction, z direction. X, theta, y, theta, z. So this is the complete velocity kinematic. You remember that in the last class, what was the dimension of your Jacobian? 2 by 2, right? Because we said, okay, in 2D, I know that the only velocities that are important for me is x and y direction because, well, it's gonna be in z, there is no other movement, right? So that was like a partial kinematic because we had information about everything else. Now, with this method, we're gonna find the whole Jacobian, all of it. And you will see that, oh, some part of it is, like you see there are so many zeros that, oh, this doesn't matter, right? So we're gonna find all of it. So our Jacobian dimension will be different from what we did in direct, because in direct, purposefully, we only stuck to the velocities that are very important. Now, my question for you is, what is the dimension of J? What do you expect it to be with that information I gave you? Math. So this is 6 by 1. This is 2 by 1. This is 1 by 6, 6 by 1. How do you say that one? 1 by 6? No, 6 by 1. 1 by 6, that's how you say it. So this is 2 by 1. Yeah. No, you say 6 rows, 1. 6 rows, 1 column. What should be the dimension of your Jacobian for this to be mathematically correct? 6 by 2, right? Interesting, because our Jacobian definitely was not that. So it's going to be a non-squared Jacobian matrix. And the 2 are because we have 2 joins. The 6 is always 6, because we always have 6 output. So very quickly, if for your class participation, what's the dimension of your Jacobian? 3. You have 3 joins, you always need 6 output. 6 by 3. Why it is good to know the dimension? It's always good to have a guess of what your solution should look like, so you can evaluate yourself as you go. Now, I don't know if you remember this part from last class or not, but Jacobian has 2 portions: linear velocity, linear Jacobian, and angular, because we have linear velocity and angular velocity. All right. Now let's calculate the v's and omegas from this equation I gave you. So we want to know what's V1 to V3, omega 1 to omega, well, I could just say V2, V3. I'll do the simple ones. So first of all, these are my axes. This is x0, y0, because I know this is my z0. That's my fixed frame. I'm gonna do this. This is my fixed frame. And then I'm gonna say that I'm gonna show my axes in this direction, so it makes sense because it's rotated. And this one also rotated. So x2, y2, so it means these are z2 in this direction. V1, this direction. And then this is my end effector, right? We will put, because we want to know the velocity here, this is x3, z, and y3. There is no rotation here, but to be consistent, I'm gonna keep z in this direction. So they're all in the same direction. Now, what is V1? Linear velocity at first join. 0. Nothing is happening. What is omega 1? Theta dot 1, right? And then you need to also show the z-axis for that. Because there's no joint before it, the joint in there, you had theta dot times the z-axis direction. What's the z-axis direction? With respect to fixed frame. Right? The z is, so we can kind of, but now at this point, all of you should be able to look and say, oh, all the z's are in the same direction. So all the omegas have the same axis, right? So all the z's are 1. So you kind of know by looking at it, what are your omegas, the direction of omegas. So we took care of the first one. This was the easy one. Now let's write the second one, V2. So if you're in the for loop, I equal to 1, now I equal to 2, I equal to 3, so you're solving it multiple times. Now for V2, we have V1 plus omega 1 cross product of P2. So let's say you can call, I'm calling this P2 and P3. So V1 is 0 plus omega 1 is theta dot 1, 0, 0, 1, cross product of, okay, here you have to find this distance and this distance in Y frame, in frame 1, because we are finding it in that same frame that they are at. L1 cosine theta 1, and then I'm gonna write C1, so, and then L1 sine theta 1. And then 0 for z. So C1 is cosine theta 1, S1 is sine theta 1, just shorthanded. All right, now, this, I don't actually have to do it. You can use a skew symmetric if you wanted and solve that. When you're using your code, you don't have to actually do that. It will do it for you. So I found V2 and omega 2. What is omega 2? Omega 1 plus theta dot 2 times multiplied by the direction 0, 0, 1. So what is omega 1? Yes. So you're going to replace that there. So we basically wrote an algorithm for our problem to solve for Jacobian, for velocity kinematic. Now, since the direction of your z's are the same, I can factor out 0, 0, 1 vector, right? And add the two velocities together. Would this make sense? Like, does this operation make sense to you when you look at the robot? Michael, what I did here mathematically, what does it mean looking at the robot? What could I find? What does it mean? They are the same direction, right? So the direction is the same, their velocity, you can add the angle. So if this goes 15, this goes 35, they are the same direction as if this went there 45, right? So omega 2 is defined. Now we have to do the third one. So I have to move to the next one. Now here, be careful. Everyone wants you to listen up. Now, your last frame, is this a joint? No, it's our end effector. So I said last, so we had 2, but we needed to find the velocity at our end effector. So for velocity kinematic, we are not done when we run out of the joint. You have to go and find the location of the end effector. Then you have to find your linear velocity and angular velocity there. Now, what is the linear velocity there? It's V2, right? The previous plus omega 2 cross product of P, let's say 3. That's what they call. So 0, 0 theta dot 1. I'm gonna just copy from here. Plus this omega 2, this guy, cross product of, now this distance. This distance is L2 cosine of theta 1 plus theta 2. So cosine 1, 2 is cosine of theta 1 plus theta 2. That's the shorthand that you can use, and I would understand that. This one is L2 sine 1 and 2 and 0. So that is your V3, all of that. Omega 3, omega 2 plus, right? The previous angular velocity plus what? What's the angular velocity at the end effector because of the end effector? 0. It's not a joint. It doesn't. So your last one, your last angular velocity at end effector is just whatever was before. So it's plus 0. So whatever is omega 3, omega 2, which is that guy over here, copy, paste. So I'm going to put boxes around things I need. V1, omega 1, V2, omega 2, V3, omega 3. Now, J is JP over J omega. All the linear velocities and then all the angular velocities. Let me see if I can do this seamless so we can still see what happened up there. So J is JV and J omega. All right. How do we write this one? For this one now, J omega is all, so it's a mapping, right? We're gonna put the axes. How many joints do we have? Two. We have two omegas, omega 1 and omega 2, right? So what we did before was calculating all those values. This is how we create the equation. So we have to put omega 1 and omega 2 here. What was omega 1? 0, 0, 1. So this is your omega 1. And then omega 2. Omega 2 was 0, 0, 1. So the good thing about this method for Jacobian is that you could write J omega part of the Jacobian by looking at the robot. Because you just need to know what's the direction of the angular rotation, right? It's the easy part. Everything else we did is for JV. Now, if you solve all of those that we had on top, your JV becomes this. Negative L1 sine theta 1 plus, you guessed it because we already seen this in the previous class. S12, L2, S12, L1 c theta 1 plus, so these are cosine sine. L2 sine theta 1, 2, L2 cosine theta 1, 2, assuming that I wrote all of these right. And then these are zeros. Now, what do you see here? This is the one we found, x, y direction. This is 0 in z direction, right? There was no velocity in your velocity direction, correct? So if you like to look at the end effector, it only has velocity in x and y direction. Now, if I put them all together, but you have the annotated version, so if you want to listen, because I think listening to this would be probably more important than actually writing those. Now, you have to do this. You have to put them all together now. I'm going to cheat. The linear velocity part, the linear part of it is at the top, then 0, 0, 1, 0, 0, 1 for the angular part. Now you have 6 by 2. So your x dot is JV, J omega, which is that times theta dot 1, theta dot 2. Now, do you remember that you found singularity for the robot? Talk about it a little bit. Now, look at this. This is 6 by 2. Can you calculate the determinant for this? No, right? So this is where you have to actually think about what is or what is the configuration. What can we do based on what you could do in last class? What could we do to this matrix? That's right. It could look like what we had before. If I eliminate all of this, becomes that matrix, right? So you can use something called reduce Jacobian. So every one of these parts are called ends, something that you can separately find that one and this one, and find the determinant multiply. Or you could use reduce, you can reduce it, but you need to know that this is what you did. All right, so when you find the solution, you have to look at the robot. Does it still make sense? Now, for the robot we had in last class, 0, theta to 0 was one of the singularities, right? Do you remember the robot? It's the same robot we're talking about, right? This was theta 2. This was theta 1. So one singularity was this configuration. Theta 2 equal to 0. We said this is one of the singularities. Because now that your theta 2 is 0, what happens to your robot? How does if only theta 1 moves and theta 2 is lost? You converted from 2R robot to what? 1R. So you took 1 degree of freedom out of it, right? So the definition of singularity is if you remove an ability of the end effector. So the end effector might not be able to reach all the configuration, not just the position that was possible with this robot. Now, what was the other singularity? Some of you answered right, some of you totally ignored answering singularity. What is the other one? What's happening there? So it's funny, but try to do it. Doesn't matter what theta 1 is, your end effector is fixed at the frequency, right? So my shoulder is so you totally took all the freedom out of yours. So you have a joint, you have a motor that moves, but nothing changes. So that's your other singularity. Now, if you find the determinant, you should find this similarities, but sometimes just looking, most of the time, actually looking at the robot, you can tell what are the similarities, and you want to avoid it. So when you are sending this robot to position, you will exclude 0 and 180. You go close to it, but you exclude those numbers. Yes. But yes, so singularity is when the end effector loses a position or ability to move, right? Ability to move. Now, a case could be losing a degree of freedom, or in this case, it does not move at all. Doesn't matter how much you move the. If this was an actuator, it doesn't matter how much it moves. The end effector doesn't want to. Now, sometimes you see that, especially if you're familiar with gimbal effect, when two axes align, you lose a degree of freedom there because nothing will change, right? So when we talked about polar angle, something that you need to be very careful about is also singularity, because from axes they will align because you have x, y, x. If the two x's are aligned, you're losing one of the two. So if you don't know gimbal effect, I'll post a video on those, like on that lecture that explains gimbal effect. Especially when you have cameras that's trying to record and they're moving around, they avoid. What you do with singularity, you avoid that configuration. So if you're coding, your angle will start from, so it's not 0, it's parentheses 0 until parentheses 180 and then 180, parentheses 180 to whatever. That means that excludes. Does that make sense? So you have to consider that in your robot. Any questions on all of this in general? Yes.
So in the singularity, or we're saying the singularity only occurs, let's say you have 1 set angle for a joint, or could you have at 5 joints? Would it be an unfold setting?
You could have singularity in different joints. It could be because of a value to it and a specific data singularity happens, or the axes are such a way that they can align and then will be redundant, nothing will move. So if let's put joint, right? So this my arm can move, right? This orientation look at the end effector. If this is 0, if these two are aligned, the only thing my end effector does if there was a motion. But then now like here. Because I can rotate, I'm rotating, but nothing is actually happening. So the motors are working, right? And this is because of this alignment, this position. So usually you will see the effect from some angles, but it's because the axes are aligned this way. That doesn't matter how much I'm moving. So these two is not moving, right? So singularity could be for partial, because you say, okay, move your elbow. But I'm talking about this orientation. If this was 0, and then my shoulder doesn't matter what it does. This would stay. Sense? So When I was talking about how to develop the Jacobian from V and Omega, a lot of you didn't have any feedback on your faces. So I'm assuming it's Friday, you all need to rest. But you really need to look at this on the weekend and do the assignment yourself. So study it, close, try to see if you can do it, because next class, I'm actually telling you how to write the program. Right, so you need to really understand what happens. Yeah, and that's it, you can leave if you have to. I'm gonna pause this, hold on that thought.